everyone. All right, so here's what notes 3 should look like. So we're going to talk about writing equations using exponential functions and the situations that surround them. So the first things that we're going to discuss are the growth rate and your decay rate. It's really important to understand what those are because the Regents does ask about them sometimes. So growth rate is usually some percent given, which indicates growth. So like it's a percent given when you have like population that increases. So I'll do my little arrow increases, or a percent given when we're talking about interest, or a percent given when you're talking about like Ebola, not really, but like a disease, spreading of disease, which we're all very familiar with at this point with COVID, or something, ridiculous like zombies. They tend to grow super fast in population. So, but the main thing is you understand is that it's a percent given that indicates growth. Okay, so when you have populations increasing or you're earning interest on money, that's growth, and then the percent given is the growth rate. So same thing with decay. It's again a percent given, but it's the percent given that indicates decay. So like we've talked about half-life. We've talked about depreciation. If I could spell it right. Depreciation. Or a population being eliminated, like endangered species, or a city's population is declining, things like that. So I'll even put underneath it, population decreases. Okay, so to find the exponential base, which is different from the rate, okay, so the growth rate and the decay rate are a specific percentage, like it's growing at 5% per year, or your car is depreciating at 3% per year. The exponential base here is the base of your function, the base of your exponential function. So when you're talking about growth, that percent given, I'll use green because that's what we're using for growth. So green, the percent given, this is the growth rate. And to get the base itself, you're going to add that to 100. So an example I'd like to use is, say you're given a growth rate of 4%. To find the exponential base, you would add 100% plus your 4%. So your base would be the decimal equivalent to 104%. Okay, so it would be 1.04 raised to the x, okay, which is what this last part is saying, is change the percent into a decimal. So then same thing for decay. Decay, your decay rate, or your rate of decay, okay, decay rate, or the rate of decay, that's the percent given, and you're actually going to subtract that from 100%. So again, let's say we had a population decrease, like an animal population decrease of 5%. We would take the 100% and subtract the 5%. So we'd end up with 95. Okay, 95% of the population is left. And that would be your exponential base. So exponential base. And then you turn that base into a decimal, so 0.95, okay, which is that part right there. Okay, so the base, the exponential base, and the rate are two different things. So it's very important you understand the difference between them. So make sure you have that stuff written down. So this next part, we're going to find the growth rate and the decay rate for each of the situations and then solve for the exponential base. So for number 1, a car depreciates at a rate of 12%. So a car depreciates at a rate of 12%. It's depreciating, so we know that means decay. Okay, so we can say that it's decaying by 12% per year. So this is our rate right here is 12%. And then our base, okay, we always indicate our base for exponential functions with b. So to find our actual base of the function, because it's decay, we take 100% minus 12, and that gives us 98%. Put my percents in there, okay? Which means as a decimal, not 98, it's 88. You're probably like, no, 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 Mrs. Conine, that's wrong. It's 88. And then that base as a decimal is 0.88, okay? So like if we had an equation for this, like just say, for example, we were writing an equation, we would see something like 0.88 raised to the x power. We don't know what this a would be, so we could just leave it blank, but the base is the leftover after the subtraction or addition, and the rate over here is just that. It's telling you how much it's depreciating, how much it's going down. So then number 2, a population increases at a rate of 32%. So this is a population increase, which indicates growth. And it's growing at 32% per year. So this is your rate. Your growth rate is 32%. And then to find your base, remember with growth, we take 100. We're going to add the 32% that we're given. So we have 132%, and then we're going to turn that into a decimal by moving the decimal place over 2 spaces. So our base of our exponential function would be 1.32. So again, this is just an example. So if this was the equation, it'd be 1.32 raised to the x, okay, because that is our base. All right, so let's do another one. All right, so interest rate in your bank account is 3% compounded monthly. So we're talking about interest rate in your bank account. So that means you are earning money, okay? That means you are earning money, so this is growth. Your bank account is making you money at a rate of 3%. So again, this 3% is your rate. So to find your base, because it's growing, we're going to take 100% and we're going to add 3% to it to find our base. So 103% is what our base will look like as a percentage, and then we change that to a decimal, so 1.03. Okay, so at this point, I would like you to try 4, 5, and 6 on your own. So go ahead and do that now. All right, so 4, 5, and 6. 5 and 6 were a little tricky, so we're going to walk through those together. 4, decay, 21%, that's your rate. Your base is the 0.79. Okay, so for number 5, it says every round, half of the tournament participants are eliminated. So you're getting rid of half of the participants every single round. So you're probably thinking, well, that's dividing by 2 or multiplying by 1/2. And you're absolutely correct. That's the idea. But when you're talking about rate, what rate is represented by multiplying by 1/2? Well, that would be 50%. Okay, so that's where we get our rate of 50% here. So then when we try to find our base, because it's decay, we take 100 minus that 50 and we end up with 50%, which means our base is 0.5, which again is the same as multiplying by 1/2. So I don't want you to get confused on where that's coming from. You are saying the same thing between these two, but because we are asked to find the rate of decay right here, we have to give them some sort of percent. Okay, and 1/2 as a percent is 50. Okay, so that's where that 50 comes from. So then 6, the amount of bacteria in your Petri dish doubles every hour, which is growth because it's getting bigger. So the amount of bacteria is growing. And it's doubling every hour. So if it's doubling, if you start at 100%, if you start at 100% for your first hour, your second hour, if it's doubling, you should now have 200. Then if it's doubling again, you should have 400. And then another hour goes by and you have 800 and so on. So if you're looking at this, you're like, well, I'm multiplying. If it's doubling, it's being multiplied by 2. And you're absolutely correct because that is what our base is. Our base is 2 because it's changing. It's getting multiplied by 2 every hour. It's getting doubled every hour. But we have to find the rate, the growth rate. Okay, so the growth rate is whatever percent is changing, and here it's changing by 200%. Okay, and that's how we're getting that information. Okay, so when we have our rate, we need to get our base, and so for our base here, to get 200, we have to add 100 to itself, because you're probably like, well, where is that 100 coming from? To get a total of 200% here, we need to add the 100s together, okay? So I know this can be confusing, but we do need to talk about decay rate and growth rate. We'll do more of that stuff together in class, okay? So if you have questions, write them down, please. So the next thing we're going to talk about is writing equations of growth and decay and talking about the exponential base. And we kind of talked about this a little bit already. So we have y equals a times b to the x. Here, a is considered to be an initial value. Okay, it's a starting point. So initial, you can say, is also like a starting point. Okay, it's where you start. B here is our base. Okay, we've been talking about that for a little while, and we'll keep referring to it as an exponential base. Exponential base. Okay. But the A is referred to as the initial value or starting point. So make sure you recognize the initial value. So then an exponential base, circle growth or decay, if B is greater than 1, then it has a growth or decay rate. So when B is greater than 1, it will have a growth rate. Okay, we did discuss that at the beginning of our unit. When it's bigger than 1, it is growing. It's a growth function. Okay, it is a growth function. When we have 0 is less than b, which is less than 1, we will have a decay rate. Because remember, we talked about at the beginning of this unit that would be a decay function. Okay, your function is decaying, it's going down from left to right. So keep in mind that these properties here that we talked about at the very beginning of this unit still apply. So we're going to use this idea to help us kind of write an equation given a sentence, okay, given a word problem. So write an equation, write an exponential growth model for the situation. So we have a $24,000 car depreciates at a rate of 10% per year. So you need to ask yourself, because you have an A and a B, what value does it start at? So what is the initial value? Okay, because that's what A is. What is the initial value of the car? And then what is the base? What is it changing by? My pen's not working now. Base. What is it changing by each year? So we're going to use what we just talked about from the previous section to find B. So the first thing we need to do is find A. So the initial value of the car, you purchased it and it was worth $24,000. Okay, a $24,000 car depreciates at a rate of 10%. So then now it's depreciating at this rate of 10%. So it's a decay function, okay, which means we're going to take 100 minus our 10 to get 90%. And then we need to write B as a decimal, which is what we did on the last page. So B here is going to be 0.9 or 0.90 because that's 90%. So then when we write it as a whole equation, a whole function, we have the initial value times our 0.9 raised to the x. Okay, so that's what we're doing here. We're taking what we just did on the first page and we're creating an equation with it. So then number 8, the population of skunks in McHenry County started with 300 and increases by 4% each month. So the population, okay, the population started at 300 and increases by 4% each month. So this is a growth function, okay? So that's going to help us a lot. So our initial value here for A is our starting point. We started with 300 skunks, okay? So now we need to talk about our B, our exponential base. We are given a growth rate. I'm just labeling because this is what we've been talking about. This is growth rate. So to find our base, we're going to take 100% plus 4, and we get 104%. Change that to a decimal, and that's our base. So 1.04. Okay. So then to write our equation for this function, we should now have our initial value times our exponential base raised to the x. Okay. So I would like you to try number 9 on your own. So go ahead and do that now. All right, so number 9 is a decay function. So a stock is valued at 300, then the value decreases by 9% each year. Our decay factor is 9%. Our initial value is 300, so A is 300. To find B, we take 100 minus our decay factor of 9, which equals 91, which as a decimal gives us 0.91. Okay, and then our function is y equals 300 times 0.91 raised to the x. Okay, so we're going to go ahead and stop there. We'll do more of these together in class. If you have questions, please let me know. Have a good day.